Heather must choose a shirt, a pair of pants, and a cap for today's outfit. She has 2 shirts, 3 pairs of pants, and 2 caps to choose from. How many different outfits can she make? Very, very interesting. We could simply count this one at a time. Why don't we say 2 choices for shirts? So why don't we say shirt 1 and then shirt 2? But there's 3 pairs of pants. So why don't we draw a diagram here? Let's draw a diagram like this. Shirt 1 and then shirt 2. But in this diagram, you had some choices here. We're going to have how many choices? We have 3 pairs of pants. Let's call this P1, P2, and then what? P3 for 3 choices of pants. Over here we could have P1, P2, and also what? P3 for 3 choices of pants, right? To combine with shirt 2. Now she needs to pick on caps. So how many caps does she need? She only gets to wear 1, but she has 2 to choose from. So we could have cap 1, cap 2, cap 1, cap 2. We could have cap 1, cap 2. And so we're literally counting all the combinations that she could pick as an outfit. Cap 1, cap 2, cap 1, cap 2, and finally cap 1, cap 2. It looks like we're just counting a lot of roots. It's not a root diagram, but it's often called a tree diagram. So if you turn your head 90 degrees to your right, it looks like a tree that's growing out. I also think of it as the root system. It could be the roots of the tree, the roots growing into the ground. Let's count all our possibilities. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So with brute force, we've counted 12 possible outfits. Now, is there a quick way to get all these? Yes, there is. Why don't we let n to equal the number of outfits? Well, she has 2 shirts to choose from. And then we simply multiply it by the 3 pairs of pants that she could choose from. And then multiply it by the 2 caps that she could choose from. So there's a 2 here. There's a 2 here. There's a 3 here. There's a 3 here. And there's a 2 here. And there's a 2 here. Well, what's that? That's 12. Heather can make 12 different outfits. And circle your work and circle your conclusion. For the dinner special at a restaurant, the customer must choose a salad, an entree, a side dish, and a dessert. Here are the items to choose from. For salad choices, you can choose from Caesar, Garden, or Southwest. The entree, grilled chicken, lamb, roast turkey, or salmon. The side dish, French fries, pinto beans, baked potato, and finally your dessert, ice cream, brownies, chocolate cake, and apple pie. Well, for your salad, there are 3 choices. For your entree, there are 4. For your side dish, there are 3. And the dessert, there are 4 choices. So how do you count all the dinner specials? Well, you simply multiply all your choices. So let's let n to be the number of dinner specials, and we're simply going to take 3 times 4 times 3 times 4, and that's 12 times 12, which is equal to 144 dinner specials. That's a lot of dinner specials. Suppose we want to choose 2 letters without replacement from the 5 letters A, B, C, D, and E. How many ways can this be done if the order of the choices is relevant? Relevant. That means what we want to do is count the possible orderings. That means we want to count that the order does matter. I'll give you an example. Let's suppose that you own a business and a restaurant business, and you're trying to hire 2 waitresses, or you could say a waiter and a waitress, right? There's 2 positions open, but only 5 people applied. So out of those 5 people you interviewed, you're going to rank those 2 people. Okay, you have to rank them. In other words, you have to include the order. So that way when you call them back, you know who to call first. All right, why don't we do part A? Let's do one part at a time. There are actually 2 completely different problems. So when the order does matter, what we're going to do is count the permutation. A permutation is simply an ordering of R items taken from a sample of N. Okay? But instead of explaining it with N's and R's, why don't we go ahead and list all the orderings by using some brute force. So let's list the ordering that starts with A, or the orderings that start with A, plural, orderings. A, B, A, C, A, D, A, E. So those are all the orderings that start with A. What are all the orderings that start with B? B, A, B, C, B, D, B, E. And then what is C? What are all the orderings that start with C? C, A, C, B, C, D, and then C, E. How about D? D, A, D, B, D, C, D, E. And then lastly, we're going to start an ordering with E. E, A, E, B, E, C, E, D. So how many are there? There's actually 5 groups of 4, so there's 20. 20 orderings here, 20 rankings. Now, why don't we get 20 in a very, very different way? We have 2 positions, and we wanted to rank them. First position, and then the second position. So how many choices there for the first position? Well, if you look at your chart, out of the first position, there's 1, 2, 3, 4, 5 choices. So we simply take 5, and then out of the second position, if you already chose one of the positions and now you need the order of the second position, there's only 4 choices left to choose. So there's 20 orderings. So there's 20 orderings from 5 items taken 2 at a time. That's another way of saying this. There are 20 orderings. I should spell 20 correctly. 20 orderings from 5 items taken 2 at a time. Or we could say 20 permutations from 5 items taken 2 at a time. That's probably the best vocabulary. Now, why don't we move to part B? Part B says, how many ways can this be done if the order of the choices is not relevant? So if it says not relevant, that means order does not matter. Now, order does not matter. We don't think of the word permutation. Instead, we think of the word combo or combination. In other words, how do we join possibly these two combinations? I shouldn't say two combinations, but two positions together. How many ways can we do it? So we could start counting in a very similar fashion. We just got to make sure to realize that the order doesn't matter. So let's try AB, AC, AD, AE. Now, for the next thing, when we start with B, we don't count BA because we already counted that in the first grouping. So we're going to count BC, BD, and then what? BE. And for the next grouping, we don't count CA. We already counted that. We don't count CB. We already counted that. So we're left with CD and then CE. And then finally, in the very last, well, not finally, what happens with D? D. We already counted DA. I'm referencing up here, by the way, if you're wondering what's going on. I'm just counting the combinations of 2 choices, taken from 5. Okay? So we're going to do 5 items, choose 2 of them. Or 5 items, and we're going to take a combination of 2 of them. So what do we have left? Do we have a DA? We already have a DA. Do we have a DB? We already have a DB. Do we have a DC? We already have a DC. Do we have a DE? We have not counted the DE. So why don't we list that? And there you go. We have everything else, though. E has been combined. So how many choices are there this time? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 combinations. So with 5 items, taken, with 5 items taking 2 at a time, we have 10 combinations. Now let's look at these 2 problems in a slightly different manner. I'm going to go back to part A. And we're going to get 20 in a different way. And so going back to part A here, what's another way to get 20? We could find a pattern here. Another way to get 20 is simply by getting 5 times 4 is equal to, let's say, 5 factorial over what then? How about 3 factorial, right? Which is another way of saying n factorial over n minus r factorial, where n is 5 and neat parentheses there, and r is what? 2. So when we write n items and permute 2 of them at a time, permute r of them at a time, we simply have this formula, n factorial over n minus r factorial. So this is n items permuting r items at a time. So in this case, order matters. Now let's look at part B. Part B is a very similar computation. This time we get 5 times 4. We get 10, actually. I should say we get 10. The first one was 20. One way we get 20. So how can we get 10 from this counting exercise? We get 10 is equal to 5 times 4 divided by 2, right? But this is equal to what? This is equal to 5 factorial over 5 minus 3 factorial times 2 factorial. So this is equal to n factorial over n minus r. Let me see here. Take that back. I made a slight error here. This should be n minus r, which was 2. Oh, I did have it right. I'm just writing it a little bit differently. 2 factorial. Yes. Right, where once again, n is equal to 5, and r is equal to 2. So that's another way to get 20. Now, in general, we have this formula. If you have n items, and you want to make a combination taking r items at a time, we use this notation. We use n choose r, which is equal to n factorial over what? Over n minus r factorial divided by all the double counts. In other words, we don't want to count all the same possibilities again. And the way we do that, the way we compensate for that, is simply divide out by r factorial. So notice it is the number of permutations, but we don't want to count all the possible rankings. So we have to divide out all the extra orderings, and the extra orderings is going to be r factorial. So that's another way of looking at this. Computing permutations and combinations. So what's the difference between permutations and combinations? A permutation is a ordering. I'll give you an example. So when we say 11 permute 4, an example here would be, let's say you have a basketball tournament and there are 11 basketball teams fighting for a playoff position. And so before the tournament started, you already know that there's only 4 teams that could be in the playoffs. So with those 4 teams in the playoffs, you would have to seed them or rank them in order from 1, 2, 3, and 4. So in this case, we say out of 11 teams to choose from, we're going to permute 4 of them. And that's how we figure out how many possible permutations you can get from 11 teams, permute 4 of them. A combination, on the other hand, is a combination where order doesn't matter. A classic example would be, perhaps you go to an American Chinese restaurant. There are 12 things you could choose from for their food items. You know, there could be chow fun or General's chicken or Cashew's chicken or sweet and sour pork or fried rice, and the list goes up to 12 items. But their special is you could choose a 5-item combo. So it doesn't matter about ranking these items. The fact is you get to choose 5 of those items. So when we see 12, C sub 5, that's really saying out of 12 items, choose 5 of them, and the order doesn't matter. So hopefully that gives you some insight on why we do such computations. From a calculus standpoint, this is actually a good way to understand how factorials work. So let's recall that definition. What is a factorial? The function f of n equals n factorial for n equals 0, 1, 2, ... is n factorial is computed in this way. N times n minus 1 times n minus 2 times. And so the 3 dots mean that you're going to multiply things in this pattern. 2 times 1. So you're counting things down, starting with the whole number. And there's one other thing. 0 factorial is defined to be 1. So that is the definition of a factorial. Combinatorics are used often in a subject called statistics as well. From a calculus standpoint, the factorial function is an important function where it is studied in sequences and series. This is a function that grows faster than your exponential function. However, the factorial function is not continuous. All right, let's write down a few formulas here. The first formula is out of n items, and you wanted to permute 4 of them, we're going to write n factorial. I'm sorry. N factorial over n minus r factorial. For our specific case, we're going to do 11. Out of 11 items, we're going to permute 4 of them. That means we have 11 factorial over 11 minus 4 factorial. Oops, I forgot parentheses here. I apologize. 11 minus 4 factorial is 7 factorial. 11 times 10 times 9 times 8 times 7 factorial is now in the numerator, and put this over 7 factorial in the denominator. And so now we are left with 11 times 10 times 9 times 8, which of course can be done in your calculator, which is 7,920. So that's an example of this computation. Notice you don't need you don't have to perform it in a calculator right away. The thing we want to do now is simplify the expression. So we're going to attempt to simplify the expression 12 choose 5. So out of 12 items, we're going to make a combination of size 5. Sometimes we say out of 12 items, we're going to make a combination of 5 at a time. We need a formula here as well. So n choose r is equal to n factorial over n minus r factorial times r factorial. Now we have 12 factorial in the numerator. We would have 12 minus 5 factorial times 5 factorial, which equals to, well, let's go 12 times 11 times 10 times 9 times 8 times 7 factorial, all over what? 7 factorial times 5 factorial. 5 factorial is 120. So 5 factorial is 120. 5 times 4 times 3 times 2 times 1. That is actually 120 right here. So we are going to reduce. We're going to reduce the common factor of 7 factorial. And then we're going to reduce a common factor of 120. So what are we left with? We're left with 11 times 9 times 8. (11 times 9 times 8). So 99 times 8, which is 700. 792. Oh, silly me. The numbers are right there on the left. Suppose we want to choose 6 colors without replacement from 8 distinct colors. How many ways can this be done if the order of the choices is not relevant? If the order of the choices is not relevant. So if it says that, that means order does not matter. And that means we're really counting something called a combination. In fact, we're going to use n choose r. So out of n items, and you take you take an r of those items, we'll make a combination out of it. What about if the order of the choices is relevant? Then we say order matters. And instead of counting combinations, we are going to count permutations, and we're going to use the formula n permute r. Out of n items, we're going to permute r of those items at a time. Let's go ahead and do A and B here. A, n is 8, r is 6. So 8, choose 6. Now, if you need to, you could certainly write the formula down. N choose r is n factorial over n minus r factorial. Divide out all the double counts, or the other counts of the orderings. We got to take out all the orderings. Let's finish this off. 8 factorial over 2 factorial, 6 factorial, and then we simplify. Simplify the common factors, and we're left with 4 times 7, which is 28. So there are actually 28 combinations. In part A. For part B, how many ways can this be done? If the order of the choices is irrelevant, we're going to take 8 items, permute 6 of them at a time. And so we will have 8 factorial over 2 factorial. Oh, I should state what formula I'm using. I apologize. Here's the formula. N items permute r of them at a time. We simply write n factorial over n minus r in parentheses and then factorial. And 8 factorial over 2 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 factorial. So you can see that there's going to be a lot more permutations because we say that the order matters. So go ahead and reduce the factorials and then do this computation on your calculator. We get 20,160 permutations. Use the binomial formula to find a coefficient of the q to the 19th power times s term. In the expansion, the quantity q minus 2s raised to the 20th power. First of all, what is the binomial formula? Remember that it actually uses combinations. So one way to write it is to write it as a plus b times a plus b raised to the nth power is equal to the summation of, let's say, the combinations in this case would be n choose r times a to the what? To the n minus r times b to the r, where r is equal to 0 all the way to n. So that is the binomial expansion. You might not like that. You might want to write it this way. I'm going to write it right here. A plus b raised to the n is equal to n choose 0, a to the n, b to the 0, plus n choose 1, a to the n minus 1, b to the first power, plus n choose 2, a to the what? N minus 2, b times b squared. And you could see a noticeable pattern if you write it like this. Plus dot, 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 some terms in between, plus n, choose n minus 1 times a to the what here? N minus 1 times b times n choose n, which I know is 1. Oops, I meant to say plus. And then a to the 0 power, and then b to the n. Oh, that shouldn't say a to the n minus 1. That should just say a, and that should be b raised to the n minus 1. I fell off the pattern there. There, that's much better. Yeah, that's correct. Let me clean that up a little bit. There. All right, part A. Use the binomial formula to find the coefficient of the q raised to the 19th power times s. So here's our binomial, q minus 2s. Now we don't need to expand this entire thing. We just need to figure out how do we get the coefficient of this particular term. According to the pattern, we should do 20, choose 1. And then what is our a value? Our a value is q. What's our b value? Our b value is the quantity negative 2s. So 20 choose 1, and then we have a, which is q, times it, or raise it to the 19th power, which is what we want. And then, what about our s? B here is negative 2 times s. Raise it to the first power, which is correct. We got it. So we need 20 choose 1, which is 20. So we just get negative 40 times q to the 19th times s. Now we just want the coefficient, so the coefficient is negative 40. Circle that. Let's do part B. Part B, we're going to restart the problem. My letters for A and B in part B are going to be different from part A. Now this was part A. Let's do part B now. We want the coefficient of the term y squared raised times q to the 11th. We want the coefficient of the term y squared times q to the 11th. So according to the pattern, we want definitely a combination So we have 13. Choose what? We want y squared. So that might be a little bit easier way of looking at it, where let's say a is what? 3 times y, and b is equal to negative q. So this has to be 13 choose 11, right? And yes, that's going to work. Now we just need the coefficient. So I'm going to highlight the coefficient in a different color. This will represent part of the coefficient. We're going to have times 9, which is going to be part of the coefficient. And we have y squared. And then we also have negative 1, right? We're going to have negative 1 here as part of the coefficient. And then q to the 11th. The only thing left to find is 13 choose 11, which isn't bad. 13 factorial over 2 factorial divided by 11 factorial times it by negative 9. And then we have our variables, y squared q to the 11th. So that's going to be 13 times 12 over 2. That should be in red. 13 times 12 over 2 times negative 9 and so we have 6. 6 times 13 times negative 9. The coefficient is negative 702.